Section 1. Building blocks of matter, atoms and lattices. Imagine a single grain of salt. Now imagine breaking it in half, and then in half again, over and over. Eventually you would reach a point where you couldn't break it down any further. You would have reached the atomic level, the fundamental building blocks of matter. Atoms are incredibly small, but they are governed by the laws of quantum mechanics. These laws dictate that electrons in an atom can only exist at specific energy levels. These levels are like rungs on a ladder, and electrons can only occupy those specific rungs, not the spaces in between. Now let's zoom out from a single atom to a solid material, like that grain of salt. In a solid, atoms are arranged in a regular repeating pattern called a lattice. This lattice structure is crucial for understanding how materials behave. This regular arrangement of atoms in a solid forms the foundation for understanding the fascinating world of energy bands. Section 2. Energy levels from atoms to solids. In an isolated atom, the energy levels available to electrons are discrete and well-defined. Think back to the ladder analogy. Each rung represents a specific energy level that an electron can occupy. However, when atoms come together to form a solid, something remarkable happens. The outermost energy levels of neighboring atoms begin to overlap. This overlap is a consequence of the wave-like nature of electrons, as described by quantum mechanics. As more and more atoms are brought together, the overlap becomes more significant. Instead of discrete energy levels, we now have energy bands. These bands are ranges of energy that electrons are allowed to have within the solid. This transition from discrete energy levels to continuous energy bands is key to understanding the electrical and optical properties of materials. Section 3. A stadium analogy, visualizing energy bands. Imagine a large stadium filled with thousands of seats. Each seat represents an energy level that an electron can occupy. In an isolated atom, the stadium is mostly empty, with only a few occupied seats representing the electrons. Now imagine bringing many stadiums together to form a massive complex. As the stadiums get closer, the seats begin to overlap. The once empty spaces between seats start to fill in, creating continuous rows of seats. This is analogous to what happens to energy levels in a solid. The individual energy levels of isolated atoms broaden into continuous bands of allowed energy states. Just like in the stadium where people can move freely within a row, electrons in a solid can move relatively freely within an energy band. This analogy helps to visualize the concept of energy bands and how they arise from the interaction of many atoms in a solid. Section 4. The quantum wave in a crystal, introducing the Bloch theorem. To understand the behavior of electrons in a crystal, we need to delve into the realm of quantum mechanics. In the quantum world, electrons are not just particles, they also exhibit wave-like properties. The Bloch theorem, named after physicist Felix Bloch, provides a powerful tool for describing the wave function of an electron in a periodic potential, like that found in a crystal lattice. This theorem states that the wave function of an electron in a crystal can be expressed as a plane wave modulated by a periodic function. Mathematically, the Bloch theorem can be written as PSR equals e to the power of IKR times u of r, where PSR is the wave function of the electron, e to the power of IKR represents a plane wave, k is the wave vector related to the electron's momentum, and ur is a periodic function that has the same periodicity as the crystal lattice. This elegant theorem tells us that the electron's wave function in a crystal is not simply a plane wave, as it would be in free space. Instead, it is modified by the periodic potential of the lattice, resulting in a wave function that reflects the crystal's symmetry. Section 5. The Kronig-Penney model, a simple picture of allowed and forbidden energies. The Kronig-Penney model, developed by Ralph Kronig and William Penney, provides a simplified but insightful model for understanding how energy bands arise in a crystal. This model considers a one-dimensional periodic potential consisting of a series of rectangular potential barriers. By solving the Schrödinger equation for an electron in this periodic potential, the Kronig-Penney model reveals a remarkable result. Not all energy values are allowed for electrons in a crystal. Instead, there are specific ranges of allowed energies called energy bands, separated by forbidden energy gaps. The model demonstrates that the width and spacing of these energy bands are determined by the strength and periodicity of the potential, which in turn depend on the type of atoms and their arrangement in the crystal lattice. Section 6. Schrödinger's equation and band structure, a deeper dive. To gain a deeper understanding of band structure, we need to consider the Schrödinger equation, the fundamental equation of quantum mechanics. This equation describes how the wave function of a quantum system, such as an electron in a crystal, evolves over time. The Schrödinger equation for an electron in a crystal includes a term representing the periodic potential due to the lattice ions. Solving this equation is a complex mathematical task, often requiring numerical methods and approximations. However, the solutions to the Schrödinger equation reveal the allowed energy states for electrons in the crystal, which correspond to the energy bands. The shape and characteristics of these energy bands depend on the details of the crystal potential and the interactions between electrons and the lattice. By solving the Schrödinger equation, we can determine the band structure of a material, which in turn dictates its electronic and optical properties. Section 7. Conductors, insulators, and semiconductors. The power of band theory. Band theory provides a powerful framework for understanding why some materials are good conductors of electricity, while others are insulators or semiconductors. In conductors, the valence band, the highest energy band occupied by electrons at absolute zero, is either partially filled or overlaps with the conduction band, the next higher energy band. This overlap allows electrons to move freely from the valence band to the conduction band, even with a small applied voltage, resulting in high electrical conductivity. Insulators, on the other hand, have a large energy gap between the valence band and the conduction band. This gap acts as a barrier, preventing electrons from moving into the conduction band and conducting electricity. Semiconductors lie between conductors and insulators. They have a smaller energy gap than insulators, allowing some electrons to be excited into the conduction band at room temperature or with the application of a small voltage. This property makes semiconductors incredibly useful for electronic devices, as their conductivity can be controlled by doping or applying external fields. Band theory thus provides a fundamental explanation for the vast range of electrical conductivities observed in different materials. Section 8. Band gaps and material properties, a closer look. The energy gap between the valence band and the conduction band, known as the band gap, is a crucial parameter that determines many material properties. In insulators, the large band gap prevents electrons from being excited into the conduction band, making them poor conductors of electricity. This property also makes them transparent to visible light, as photons of visible light do not have enough energy to overcome the band gap and be absorbed by electrons. Conductors, with their overlapping or partially filled bands, have no band gap, allowing electrons to move freely and conduct electricity easily. They are also opaque to visible light, as electrons can absorb photons of a wide range of energies. Semiconductors, with their intermediate band gaps, exhibit a range of interesting properties. Their conductivity can be tuned by doping, adding impurities that introduce extra energy levels within the band gap. This control over conductivity is what makes semiconductors essential for transistors, diodes, and other electronic components. The band gap also plays a crucial role in determining the optical properties of materials, such as their color, transparency, and ability to emit light. Section 9. The future of electronics, band engineering and beyond. The ability to understand and manipulate band structure has revolutionized electronics and paved the way for incredible technological advancements. By carefully controlling the composition, structure, and dimensions of materials, scientists and engineers can tailor their electronic properties with remarkable precision. This field, known as band engineering, is at the heart of modern electronics. It enables the creation of faster, smaller, and more efficient transistors, lasers, LEDs, and solar cells. For example, by layering different semiconductors with varying band gaps, engineers can create heterostructures with tailored electronic properties, enabling the development of high-performance transistors and lasers. Furthermore, the exploration of novel materials, such as graphene and topological insulators, with their unique band structures promises to unlock even more exciting possibilities for future electronic devices. The journey into the world of band theory reveals a universe of possibilities for manipulating the electronic properties of materials, leading to a future of electronics beyond our wildest imaginations. Section 10. Conclusion: a universe within a crystal. From the simple arrangement of atoms in a crystal lattice to the intricate dance of electrons governed by quantum mechanics, the journey through band theory has taken us to the very heart of matter. We've explored how energy bands arise from the interaction of atoms in a solid, the crucial role of the Bloch theorem in describing electron wave functions, and the insights provided by the Kronig-Penney model. The Schrödinger equation, the maestro of the quantum world, reveals the allowed energy states for electrons in a crystal, dictating whether a material will be a conductor, insulator, or semiconductor. Band theory has not only revolutionized our understanding of materials, but has also paved the way for remarkable technological advancements in electronics, optoelectronics, and beyond. As we continue to explore the vast landscape of materials and their electronic properties, the journey through band theory has just begun. We've only scratched the surface of this fascinating field. Future essays can delve deeper into specific applications of band theory, explore advanced concepts like density functional theory, and discuss the latest breakthroughs in band engineering and the search for novel materials with exotic electronic properties. The universe within a crystal is vast and full of wonders waiting to be uncovered.